Now that we have the full physical law, a form of Ampere's law, that, as far as we know, represents how physical reality works, it's useful to not only have a differential form, but just as we had in the electric field case, to explore integral forms for this type of a law. To do that, we have to review very briefly a little bit of your vector calculus, a powerful theorem known as Stokes' theorem. So let me just review that for you briefly. So if we want to get this integral equation, we're going to be using Stokes' theorem. Now, Stokes' theorem is the analog of the divergence theorem, but this is the analog that works for the curls of vector fields. In this case, what we do is if we have any vector field, so for any field B, you have the following result. If you take the curl of B, that's a derivative, and you integrate it, but now the curl of B is a vector, right? So the natural integral to do with a vector is to integrate it dot product with something. And typically that's an area element. So we're going to be doing an integral over some area. And here I'll try to sketch down below geometrically what I'm doing. So it doesn't have to be a closed surface. It's just over any area. In this case here, I'll try to draw some three-dimensional looking thing. Maybe it's the top of a sphere. So I've got like this base part, but the surface I'm integrating over kind of lumps out of the page here a little bit, has some form to it. And at any given point, there's a normal vector here that I will draw dA. And that normal vector is defined, of course, as the scalar value of the area that each patch represents times the normal vector, which we typically would represent by an n hat. So what I'm talking about then is integrating over this entire curved surface that is kind of like the top of a sphere that's been cut off. So I'll represent that here in my integral then as integrating over this whole surface. And because it's the whole surface, I'm going to color it in here a little bit so we know we're integrating over all of that. If you were to do that integral of the curl, what you end up with is that this derivative gets removed by the first of these integrals. So what you're left with, again, is a single integral. So we're integrating then over somehow the boundaries of our original area. Partial A is how we represent those boundaries. And in this case, the boundary or edge of an area like this is the rim of the area. So there's going to be a certain line integral we're going to do around the edge of the area. So it's going to be a line integral around just that loop part around down here like so. And so we represent that as a line integral. And the line integral is just the field that's left B dotted with dl, where dl then gives us the path going around this boundary of the area. Now, of course, there are two ways we could travel around the area, clockwise or counterclockwise, and we need all of our sign conventions to be coherent if we're going to get consistent results. So this is what's known as a directed line integral. You usually draw an arrow through your loop around the integral sign. Here, that didn't come out super clear. Let me try that again. I'll make a bigger loop so I can do this. So a directed line integral. I will indicate that in my sketch like so. And the direction of the path you're supposed to take is defined, of course, for us by this right-hand rule, right? There are two directions we could go, clockwise or counterclockwise, but there are also two normal directions to the surface, going one way or the other way. These two have to be defined coherently, so we would say then that the normal vector is defined by right-hand rule number 2, where the idea is your thumb points in the direction of the normal vector, and then your fingers circulate around the loop in the sense about which you should integrate. In that case here, you can clearly see my thumb is in the direction of that normal vector. My fingers are trying to curl me around the edge of this surface, circulating around in this direction. So that's just a piece of mathematics. what we're going to do now is to take our new physical law in this differential form and simply integrate both sides of this equation and use this mathematical result to simplify what we find. So let's rewrite then Ampere's law. It's the curl of B. And I'm going to leave some space before and after it so we can put in various integrals. That curl of B, what our result has shown us already, what that result here has shown us already, leaving a little bit of space for ourselves, is that the curl of B has two contributions, mu naught times J, the current density. Remember, leave spaces so we can put in integral pieces, plus then our new term that we had just found, this displacement current, mu naught epsilon naught times the partial derivative of E with respect to time t. So our plan now is to integrate both sides of this equation. So let's take some arbitrary area A, such as the one I've sketched for you here, and we're going to integrate both sides of my equation with respect to A over that area A. And then since the curl of B, so I have to integrate both sides of my equation. And on this side, you can see I've got two terms, and the integral of a sum is the sum of the integrals. So I can make this as an integral dot dA for the first term, and an integral dot dA for the second term. And all these integrals are over the area A. The next thing that we do is we use our Stokes theorem. We know then the integral of the curl over the area A is just going to give me the line integral about the boundary of that area. So this becomes then the directed line integral, according to right-hand rule 2, of the magnetic field B dot dl. Now this term is a very interesting structure as well. Mu naught is a constant, and so of course we can pull that out of the integral, so there'll be mu naught. What we are left with is the integral over the area A of just the current density J dot dA. But we know what that is. Whenever we integrate over an entire area of the current density dot dA, that just tells us the total current flowing through that area. So this then becomes the enclosed current, and just like we had enclosed charge, and this represents how much current is flowing through that particular area. If you want the definition, of course, it's going to be the integral of J dot dA through your area. The second term we can treat in a similar way. Once again, we can pull all of our constants out, plus there'll be mu naught epsilon naught. Now what we have is the integral of the time derivative of the electric field over the area. Now, remember that an integral is really just a sum. So we have the sum of a bunch of time derivatives of the electric field. But the sum of a set of time derivatives we know equals the time derivative of the sum. So we have then the time derivative, and what we're left with is the sum of E dot dA, but that is just another way of writing the integral over that area of the electric flux, it turns out. Integral of those E dot dAs. So what we have here is the integral form of Ampere's law, which follows directly from the differential form. And that differential form we derived by taking Biot-Savart and simply searching for an equivalent differential equation. So that then is our next, what is known as a Maxwell equation.